Okay, chapter 4. This is chapter 16. This actually says chapter 16. So, Grant, don't get confused by that.
Chapter 6.
But this is basically chapter 4. I don't know if that has to... Oh, I printed these off too.
Page Boltzmann's constant.
Yeah, it's Boltzmann's constant. Oh, yeah. They take home exam.
Forgot about that.
I hope no one got too confused over your grades. I put your grade in, it said it's out of 100. I fixed it this morning. I have part 1 worth 70, part 2 worth 30 points. And I put in your raw score. So, and then you couldn't even see your percentage grade. And I fixed all that. So now you can see what your overall percentage so far. Okay. Yeah, mostly, well, this is going to deal with Helmholtz and Gibbs, but Gibbs ends up being the flagship one. This is actually, we're not going to really get to until chapter 5. So we're right here. We're going to see this then relates to equilibria. And so Gibbs's equation has a lot of... Now this I just took a picture out of my biochem book, the TCA cycle. So acetyl-CoA going to citrate, going to isocitrate on down through here, alpha-ketoglutarate. So the TCA cycle coming out of glycolysis and going into this TCA cycle. Why am I showing this? At the next slide, what I wanted to do is put the delta G's in here. What are the Gibbs free energies going around that cycle? Here they are. Acetyl-CoA to citrate. Now there's the delta G. It's standard under standard conditions. There's the delta G kind of under human metabolism conditions. So highly exothermic. Citrate to isocitrate takes a little bit of energy to get there. Isocitrate to alpha-glutarate, again, exothermic. The next step from here to succinyl-CoA, exothermic. Succinyl-CoA to succinate, slightly, just mildly exothermic. Almost no energy whatsoever. So when you see a situation like this, it's basically just equilibrium. It's just an equilibrium reaction. It's just it's reversible. Yeah.
A few questions. What is this, for one?
Oh, you're an engineer. I forgot. Okay, I forgot. Okay, so this is the tricarboxylic cycle in biochemistry, where glucose is being metabolized and feeding into this cycle metabolism, human metabolism.
So do you make citric acid in this cycle?
Well, these are all intermediates in this very important process going on, and it's very interconnected with other things that are coming off and producing energy to make ATP and all that sort of thing. So these are metabolic steps in the body.
And then what was the difference between the delta G on that sign page and a delta G with like the degree sign?
Yeah, that's a good question. So the delta G would be kind of an experimentally in the laboratory at certain concentrations. That's what you're, and this is more under natural conditions in the body.
Okay.
So there is a difference, and we'll probably come back and relate to these slides some more. But just to make the point that the Gibbs free energy has really some broad implications and is utilized in a broad range of things, and particularly in biochemistry. It is a critical factor to decide what's going on in these reactions. So do they occur easily? Do they require a lot of energy? Okay, so the body has to invest a lot of energy to go from the malate to the oxoacetate. It needs to really invest a lot of energy. Some of these other steps here, they reap a lot. The body reaps a lot of energy. It's very easy to do that. It doesn't necessarily mean, well, it still needs to be some controls on all of that. And there are. But that's just to introduce it. Okay, so in chapter 3, the author started talking about spontaneity, what will happen spontaneously, and that's where we started talking about entropy, but he also pointed out that isn't the whole picture. The system is spontaneous if the surroundings are not required to perform any work on the system. It'll happen spontaneously. If you take a hot metal and put it next to a cold metal, spontaneously heat will flow. Heat will flow from the hot to the cold. It will not flow in the reverse condition. You can't put two pieces of metal together and expect this one to get hot by spontaneous flow of heat into one of them from the other one. So that's not spontaneous. So rock falling, an aerosol can releasing, sodium reacting with chlorine, they all move from higher to lower. Higher gravitational potential to lower, higher pressure to lower, higher chemical potential or energy to lower. So it's always kind of moving from higher to lower. But is that the only condition for spontaneity? And the answer is no. And I mentioned the ammonium nitrate. It does not release energy to dissolve in water. It actually absorbs energy, but it dissolves in water. So what's going on here? It is increasing entropy. Entropy is increasing here. We're going from a very highly defined crystalline solid to all these ions floating around in a solution. So there's a decrease in energy. Decrease in energy is inadequate for predicting spontaneity. So methane burning releases energy. Water, acid reacting with a base is exothermic. Water going from a solid to a liquid is a positive delta H, and ammonium nitrate, you got a positive delta H. All right, we said if entropy increases, then it's spontaneous. If there is no work and no heat involved, adiabatic. But this is a limited situation. So looking at internal energy is an option if volume and entropy are constant. Enthalpy is an option if pressure and entropy are constant, but those are limited, and so it enters Helmholtz energy, defining new ones, and you can probably put 3 equal signs here, 3 bars. Helmholtz is defined as the internal energy minus T times entropy. And the Gibbs free energy, G, equals the enthalpy minus T times the entropy. And we often focus on the Gibbs, as I mentioned, because it's temperature and it's an option when temperature and pressure can be controlled. And these are the most typical variables that we can manage in a laboratory. All right, again, some spontaneous things. These become more random. That will happen spontaneously. This going to that will not. It's more highly ordered. So a reaction is spontaneous in one direction, but it is not spontaneous in the opposite direction. So, looking at spontaneity. So delta G is equal to the delta H minus T delta S. There's going to be a temperature dependence on this whole thing. And we're talking absolute temperatures. Absolute temperatures. So a delta G under one set of conditions can really be different under a different set of conditions because of the temperature involvement here. All right, we already talked about this. Boltzmann's looking at the degree of the number of ways that you can arrange components of a system and getting this fundamental equation. Entropy is equal to the Boltzmann constant times the log of the number of ways of arranging it. All right. If delta G is negative, the reaction is spontaneous in the direction that it's written. Delta G is positive, it's not spontaneous. It would be spontaneous in the reverse direction. And delta G equals 0 is an equilibrium situation. So if you rewrite an equation in the opposite direction, you're going to just change the sign of the delta G, like we did with delta H's. Okay. Well, let's do an example on delta G and put this in a slide, but I'm not sure. Here we go.
What is this whole low T and high T thing?
What?
What's the whole low T and high T thing?
Well, just low temperature, high temperature. I guess you know, relative to what is a good
Yeah.
question.
It's a little like
Right, it's a little
you can just plug in
ambiguous.
the numbers and then it'd be easier
So,
to understand. But yeah.
Right. So just as low temperatures, that becomes small, then you're subtracting a small factor there. And so if delta S is positive, delta S is positive, you got a low T, you're going to end up with a positive delta G. Yeah, that's probably not a real useful slide. You're going to need to say relative to what. And I don't think it's just relative to this. But very low. Let's look at a problem. Take out your calculators, and I guess I can put it right over here. I think I had this. Where did I put this? Oh, let me see if this is on one of these slides. That would be beautiful, but I don't know that it is. Oh, yes it is. Here we go. Here we go. Here we go. It's just a few slides on here. Where is it? Yeah, I think this would be a useful exercise for right now. Oh, it's not. There it is. There it is. Okay. Let's work through this. There's two ways of calculating this. Determine the delta G of reaction for the following chemical reaction using both methods for determining delta G. Show that they yield the same answer. Okay, what are our two methods going to be? One is going to be use the equation delta G equals delta H minus T delta S, and the other method is going to be delta G reaction equals the sum of the delta G's of the products minus the sum of the delta G of the reactants. Okay, so that's what's meant by the two methods. And let's see if we have everything we need right there.
You got temperature.
Yeah, we have temperature, we have the entropy, we have the delta G's of formation, which is what we need over here. Got the delta H. Yeah, okay, so in order to do this one, we need to calculate the delta H of reaction, and we need to calculate the delta S of reaction, and then plug those into this equation and get our delta G by this equation. So it's cumbersome for me to write in here, but so the delta H of reaction is what? It's going to be the sum of the products minus the reactants, rather than write that all out there. Sum of the products. So we're in this right here, 2 times negative 285.83 minus 0. right? The delta H of the reactants. So what is that? That's negative what? 285.83 times 2. Five something.
When you're doing the calculation, delta A, or the S values are in joules. When you're doing
Yeah,
the calculation.
I'm just doing the delta H right now.
Oh, I know. I was just telling. I just tried to do one of them, and the other ones are in joules. The other everything else
Oh,
is in
okay.
joules. It's really confusing.
So the delta S of reaction is going to be, again, the sum of the products minus the reactants. So 2 times 69.91 plus or minus minus 2 times 130 plus 1 times 205. So delta S of reaction is negative 326.68 joules. Okay, joules K, right? But see, now you're going to multiply that by T. So yeah, we got kilojoules there. We're going to multiply by T. So delta G equals the delta H of reaction minus T, which is 298.15, times negative 326.68.
You have to do a conversion change, right?
Well, this,
Yeah.
this is going to be, we could, if you want to, make that point, right?
Yeah, that's what
Make that point.
I did it the first time, and then I was like, this does not seem right, so I went back and had a look at it.
Is that better?
Yeah.
And we get something like, you got a final answer?
Negative 474.26.
And let's see, our units are going to be kilojoules. All right, and then this one over here, delta G of reaction, doing the sum of the products. All we got are product. The reaction is 2. And so this is getting the and that is negative 474. All right, so the two approaches to it, and they both end up at the same place. The table I gave you on the exam had the delta H's, it had the entropies, and I believe it also had the delta G's. And there may be one other thing on there as well. But at any rate, yeah, all of those are there, and the standard thing for all of these calculations is the sum of the deltas of the products minus the sum of the deltas of the reactants. whether we're doing delta G, or we're doing delta H, or delta U, or delta S, it's always products minus reactants. Okay. All right, we really kind of are dipping our toes into the start of chapter 4. You can look back through here on the Helmholtz energy and some of its derivation, the Gibbs free energy and its derivation. We're going to come up to the Maxwell relationships on Monday. And page 103 is where we get this DH equals TDS plus VDP. I'm not sure that's shown up anywhere else in the book so far, but there it is there. It might have appeared in chapter 3. I'm not sure. It's the first time I noticed it was right there. All right, and we'll move on into this chapter. Compressibility factors will come up again later in here in chapter 4. And like I said, I'll put together your homework assignment for this chapter and give it to you on Monday. All right? I don't think I'm going to take it any further than that for Friday.